welcome Hassan, who is the new PhD student together with Ioannis, supported by the Marie Curie Safer Up project. I would like to thank Alvaro for the big work and also super high quality work that he has done for preparing the lessons. I hope you enjoy. Just some, let's say, small and pleasant information about the dinner for tonight. I believe all of you were informed that we are organizing tonight a dinner of the course, thanks to several projects and thanks to Rahib that brought Alvaro here this week. I don't know if there is anyone that already has given, his or her availability and is not coming, but we should be all participating except for you, except for Laura, who is not in a good shape. All the others are coming. Hassan, you are welcome to come if you want. We are going to the city center. All of them already know where to go. And the dinner will be at about 8, if you don't mind, 8:15, something like this. And we will be all together. So thank you very much again and enjoy the lectures.
You don't miss the dinner, it's the best part of the course.
Exactly.
Okay, so we will start from what we left yesterday. If you remember, we were doing, this was the summary of how we solve all the equations so yesterday we were talking at the beginning why we need simulation, then we start drawing things in the blackboard about equations and so on, just to express all the physics in a way that the computer can understand, right? So, but at the end, we said, okay, now we are going to solve, and as you can remember, what we are solving is that each node, to solve the energy balance of each node, the new temperature of the node just depends on the temperature of the neighbors, of the node that they are in the neighbors. So we have been dealing with these equations and applying energy conservation to each node. And then we figured out that, okay, if I was in the fin, for example, and I want to have the temperature of node number 2, if I don't know the temperature of node number 3 and number 1, I cannot get it, so I need to do something, some trick. The trick is to do the assumption. So if you remember the program, and now after that I will go here to the software and I will explain you which parts of this algorithm are how we implement it and how we program it. Basically, we put parameters, geometry, boundary conditions, numerical, like how much maximum error do I allow, how many numbers of nodes do I want to discretize my domain. I calculate the coefficients that I will need in the further equations, like areas, like volumes, like positions of the node in the fin or in any domain. Then, before I start with the equations, I say, okay, I don't know what are the temperatures in all nodes, but I assume they are whatever, T0, 70 degrees, 50 degrees, 0 degrees, whatever you want to start with. And you apply assume map of temperature. Then you go to the equations. For I equal to 0, you have one equation. For I equal to 1, you have another equation. I equal to n, you have another equation. So you compute the temperatures 0, 1, and n. Then you compare. Okay, the map of temperatures that I got from the solutions is different from what I assume. Asterisk stays for the assumption map. Okay? If the maximum deviation between those two vectors, those two arrays of values, is higher than the maximum error I want to allow, let's say 10 at the minus 6, 10 at the minus 5, depends. If yes, if it's below this error, then we can do final calculations. Final calculations means compute the amount of heat dissipated by convection. Because now I have the real distribution of temperature inside my fin. I know the temperature of air. I can know all the convection that has been dissipated to the outside. So I know how effective is my fin. Right? This is the final calculation. At the end, usually map of temperature is what you need, but you need to compute something else after you have the map of temperature. Okay? So this final calculation and then end. We can go for dinner. Okay. What happens if the maximum deviation between the solution temperature and what I assumed is not the same? If it's not the same, I have to refresh my assumption. I assumed everything was at 70, I went to the equations, and it was not the case. One node is at 61, another node was at 58, they are not at 70. So my assumption was not correct. I need to adapt the assumption. Yesterday I said, okay, now my new assumption is the solution I got directly, right? And then I pass again, forget about this now. Yesterday I said, the new assumption was my solution, okay? And then I recharge and go to calculate again the temperatures. Remember that inside the equations of the temperatures, there are assumed values. Because when I am calculating this node, I am assuming what is the temperature of here and what is the temperature here. I need to assume. Otherwise, I cannot calculate the value of the node, right? I need to assume what are the temperatures of the neighbors. Otherwise, I'm lost. So, okay, I assume again. I calculate. Again, I have one solution, one assumption. Is it the same? No. Okay, now the solution is going to the assumption. Calculate again. I have another solution. Is it the same? No. Do it until it's the same. It's the same, go home. Okay? This is the principle. Everybody understands that? This is very important. Now, if you directly charge the solution vector to the new assumption, sometimes you can get convergence problems. If your problem is very simple, it's very basic, like this one, it's okay. You will go fast and you will get the solution directly. But sometimes it's very useful to relax. And that's, there is a tool which is named relaxing factor. This relaxing factor is this term R and comes from 0 to 1. We have three groups. We have group which is solution, which is, we have a group, a map of temperature, which is assumption. Right? We have solution and we have assumption. Map and map. Now, the new assumption was directly the solution. Right? I mean, we are in iteration number 0. First iteration. We got, okay, as now. Let's say assumption. We assume one map. We calculate the solution. Is it the same? No. Okay, I need another assumption. Yesterday, the new assumption for the second iteration was directly the solution. Right? Now, what I propose is for the new assumption, assumption number 2, it will be a mixture between this solution and this assumption. It will be a weighted. Usually 80% this value and 20% this value. That means the relaxing factor is 0.8. Usually for energy equations, relaxing factor is 0.9, 0.8. Usually. So now, with this new assumption, I will create the solution because I passed through here. Now, is this the same as this? No. Okay. Then, with the mixture of that, create the new vector, assumption 3. Do you understand? So, the new assumption of every iteration will be a combination between the old assumption plus R, which is the relaxing factor, 80% for example, and the difference between the solution and the old assumption. At the end, this is a equation to mix this. If this is 1, I am just using the solution. If this is 0, I am not advancing. you cannot put 0 in the relaxing factor. Because then you are always assuming the same. So you don't advance. Okay? Everything is clear?
Yeah, okay. And how can I assume a value for my relaxing factor? I mean, R is a number between 0 and 1.
Yes.
And so, what criteria I have to apply to understand what's the best?
Maybe there are no best.
Okay.
There are no best.
Just
What happens here is imagine I have a problem with a single node. Well, a single node. Okay, this is the graph for one node, node number 3. Real solution is here. Okay, but we start. I assume that the temperature of 3 goes here. Now, it gets a solution. Pass through the equations, now it's here. Normally, it goes like this. Until it gets. So it's getting closer, 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 closer. I mean, approaching, 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 pass, go back, pass, go back, da, 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 until it gets the solution. It goes like this. So if you start here, you get closer, you pass, you go, until you get the value, right? If you don't relax, it can happen if your physics are not very simple, that you stay like this. And you don't get to the solution. And you don't converge. You stay jumping over the solution. If you relax a little bit in the energy equation, you will get it. So, there is no, if you relax, you will, usually you will need more iterations to get the solution, but it's more probable that you get the solution. So that's why if the problem is simple, don't relax. You can put R equal to 1, and you will go the most direct way you can. But if there are, I don't know, for example, in the film issue, if the heat transfer coefficient depends on temperature film, right? Like, remember yesterday we have this case. Now heat transfer coefficient here was fixed. I don't know, 25, I don't know what was the value. What's fixed? Physically is not fixed. Physically it depends on temperature of the air and temperature of the node. And you have to compute physical properties of the air at film temperature. So for each iteration I need to calculate H. Do you follow me? So it's getting complicated. If you apply this physics, then the problem is not that simple. Because for each iteration, you assume one temperature of the node. For each node, you will have different heat transfer coefficient. Because you will have different Nusselt number. Because density is different, viscosity of the air is different, everything is different. Because film temperature, meaning the average between solid and the air, is different. Right? Don't worry, the computer will compute for you. You don't have to do these calculations. You just have to program it. But that's a good example on how a good assumption can give you a good benefit. It's very important that heat transfer coefficient here in natural convection depends a lot in the temperature of the film, but we can assume a constant value for your work, for what you are dealing with that. It's very important if heat transfer coefficient is, let's say, 25 watt per square meter Kelvin, or 23 or 27, or it's okay. I can go on 25 and just go with constant. Because if it is not constant, you're adding a lot of trouble. Well, not a lot of trouble. You're adding more work to your software. Like for every iteration at every node, it has to compute Nusselt number, it has to compute heat transfer coefficient, depending on density, on viscosity, and conductivity of air, right? And then it doesn't convert. Go here. No. Okay. Another map of temperature. Another set of heat transfer coefficients. Recalculate, recalculate, recalculate. So that means that if you put constant, maybe it's 1 second. If you don't put constant, maybe it's, I don't know, 10 seconds. Okay. You can say, okay, 10 seconds is fine. Yeah, it's just a thing. Go and simulate one full heat exchanger. Then the difference will be between 30 minutes to 7 hours. I don't know. So can you assume this that it's constant value or not? That's why the message from yesterday was important. Okay? If you think, yeah, it's very important because I want to be sure that this part, because it's warmer, has higher heat transfer coefficient than here, okay, then do it. But be sure that all the complexity that you are adding to your model is mandatory, is required. Otherwise, you are wasting resources. Okay? Any question?
So, when the number of iterations increase, does the R stay constant or does it change according to?
R usually is constant.
Okay.
You fixed. I recommend you to put it as 0.9, for example.
For a certain problem, you fix the R and then let it calculate.
If you see that you have convergence problems, try to relax more your system. It's a good tool to do it.
So that R is good for the entire problem.
Yes. In any case, like mass conservation and momentum conservation usually uses 0.6 as a relaxing factor, 0.5, 0.6. Because the physics are more difficult, more complex, so you have to relax it more, not to jump over the solution. Okay? But energy equation usually 0.9, 0.8, it's okay. So is this clear? Yeah? Okay, now, I want to, before we go to the transient, I want to translate this into computer, okay? You're using MATLAB, or we are using C, okay?
I'm also familiar with C++.
You also, okay, perfect. Now, the model that is written there is this geometry. It's a new one, okay? It's not the thing, it's a, let's say a wall, or a plate, in which part of the plate has a generation of heat, let's say processor, whatever, and part has not. Both materials have the same thermal conductivity, everything is adiabatic, so it's well insulated, except one surface in which we have air at 25 degrees, with a heat transfer coefficient of 10 bar square meter Kelvin. The maximum error I want to allow is 10 at the minus 6. The number of nodes in the first part of a material is 10, and in the second part of material is 10 also, but it can change. Now it's also a good example to see how we discretize two solids differently. Imagine like this is one material and this is another. Maybe I want to add more nodes in one material than in another. Usually, you need more nodes depending on the gradients that you expect there. Like if you think that the gradients between two nodes will be low, you can reduce the number of nodes. If you expect high gradients, like for example in boundary layers, right? Everybody, I don't know if you have used, you know what is boundary layer, right? Of fluid boundary layer. You know that there are a lot of gradients in the first parts of a fluid flowing through a surface. In the first, you need a lot of nodes to capture this effect. Here in the potential area, you need less nodes because temperatures are more similar. Remember that when we discretize, we are assuming that the whole node is at the same temperature, at the same velocity, at the same pressure, at the same density, right? So can we assume here that in 1 centimeter we are having the same velocity? No. Because we have something physical that is boundary layer, stack effect, whatever. So there are huge gradient in 1 centimeter here. But here, can we assume 1 centimeter? Maybe yes. This particle of air has the same velocity as this one, more or less. We can assume that, but we cannot assume here. That's why we need more nodes here than here. Do you follow me? Yes? Great. So, if you think, okay, I have a solid, for example, or whatever domain, and what will be the temperature gradient, or because we are in temperature now, what will be the temperature gradient in this domain? Okay, we will experience a lot of gradients because it's a processor with a lot of heat. Okay, then you need a lot of nodes to capture this effect. In a building wall, you don't need a lot of nodes because there are no spectacular heat flows. How many bats does it close building wall? 6, 7 bats square meter. There is insulation. Maybe in the first parts of the layer outside, you need more nodes because of solar exposure and so on. Right? But sometimes you can have homogeneous discretization and sometimes not. It's up to you. Yesterday we talked about how to deal with homogeneous grids. I had a film and I divided with the same delta R. Here we will have 2 delta R's. Here 1. Sorry, delta X because it's Cartesian coordinates. And here 2. Actually, this thickness is 5 centimeters, this thickness is 10 centimeters. And I want to use 10 nodes here and 10 nodes here, or whatever, or 100 or 1000, up to you. I don't care. So the dimension of the node here will be 5 millimeters, and here it will be 10 millimeters. Correct? Because the thickness is different. I know the drawing is not very good, but this is 5 and this is 10. Okay? 5 and 10. So you can change. And why? Because I assume that because here we have generation of heat, we will have more gradients here than in the other part. That's why I added more nodes. This is just an example. Usually I will use more than 10, but it's okay just to show. Okay? I have a problem because I want to... right. Okay, now, yesterday we had 3 different types of nodes. Node number 0, because it was at the base, had one equation. Node in the middle, between 1 and 6, has another equation. Conduction, conduction, and convection, right? And the last one was different because it has not conduction to the east. Do you remember? Now, how many different nodes do we have? 3 nodes? Which ones are?
The one on the adiabatic layer.
This one?
And the internal.
Here?
Yeah. And the one on the right layer with the convection.
Here? Anyone else?
Between in the middle of B.
Anyone else?
And another one
Middle B.
in
Yeah.
this layer.
Because here there is no QE and here yes. So the equation will be different. Also the equation will be different here. Because we will have half of the node will have generation of heat, half of the node will not have. So the equation is different, the physics is different. Right? Usually you have the number of nodes, when you have a domain, put one node in every edge. And then inside your materials. Like, if you have, let's say, a 2D box, this is material A and material B. This is, I don't know, copper and this is steel. 2D problem. How many nodes do we have? I cannot play with symmetry here. There is no symmetry neither in this axis, neither in this axis. Right? I have one node here, I have one node here, one node here, which are different completely. This is in a corner, so the volume is 1/4. This, the volume is half. This is 1/4 again. Then I have another type of node which is in the edge. Here also, here also, here also. These ones. Those are different type of nodes. And I have to write the energy equation for each type of node. This is just one node. These are n nodes. The type of this is n nodes. I mean, this node is the same as this one. Not the same. I mean, the same equation describes the temperature of this node. So there are multiple nodes that it will perform as this one. As yesterday, the node from 1 to 6. Remember? Because we are inside something, we can program a loop and the computer will say, okay, from here to there, apply the same equation. Of course, with different neighbors, but the same equation. Here it's unique. This also, there's some nodes here. Unique, some nodes, unique, some nodes. So, you see? There are some equations that you just type for one node, but there are some equations that are inside a loop. It's the same as here. I equal to 0, I will create the equation just for this node. Now, this type of node is for all the nodes that are inside a material. Second type of node. Third type of node is just for one, which describes the boundary between material A and material B. I equal to n. Now, any node inside B material will be described as this one, fourth type of node. And the last one is just this one, I equal n plus m, fifth type of material, node. Clear? Yes? Great. Do you want me to write the energy equation of any of these ones? Maybe I equal to m, which is probably the most interesting. I equal to m. How is the... Is this correct? This is my node P equal to n. The volume and the distances between, this is closer. This is delta x1 divided by 2. This is delta x2 divided by 2. Because we have different grid size from one side to another. Yes? Okay, let's apply energy conservation. We stick to steady state and so on. So we have this, right? In this case, what physics are behind? Conduction coming from the west, conduction going to the east. Remember, I'm assuming always, you can do whatever, heat is flowing from left to right, from bottom to top. But you can do as you like. You can put these arrows in any direction you like. Anything else happening in node N? Any more energy?
There is the heat generated.
Now, this part of volume is generating heat at this rate, 500 watt per cubic meter. So we have QB. So again, this has to be accomplished. So west plus generated minus east will be 0. Right? Okay, we can compute this. What is QV? Remember, we change derivatives to gradients because that's the trick of numerical modeling. We assume the derivatives are gradients. So, because we are in narrow, the variation of this variable can be assumed as linear. Okay? Fourier here, minus k, forward minus backward, TP minus T west, divided by the distance between the nodes, multiplied by surface. Surface, in this case, it's the same, right? Because it's Cartesian coordinates. We have the same surface of heat transfer here and here and here. We have nothing cylindrical. So we can put just S. Okay, plus QB. QB is 500 baht cubic meters, so I need to know the volume. What is the volume? The volume is this distance multiplied by the surface, because only this part is generating heat. Right? So is delta x1 divided by 2 multiplied by the surface multiplied by QV, which is the 500 baht per meter, cubic meter. Minus Fourier here, minus k, that means plus k TE minus TP divided by delta x2 multiplied by S equal to 0. You see, because it's 1D, I don't care about S. Everybody follows me, eh? No strange faces. Any strange face? No? Okay. So this is the same we did yesterday. Now I'm going to isolate TP for each node. I mean, now I'm I equal to n, I isolate TP. I will do the same for this kind of nodes. I will do the same for I equal to 0. I will do the same for I equal to n plus m. And I will do the same for this kind of nodes. And that's it. And now we can move and program this. Okay? Okay, let's do it. I will isolate. In case of I equal to n, TP will be k divided by delta x1 multiplied by t west plus k divided by delta x2 multiplied by te plus qv multiplied by delta x1 divided by 2 and everything divided by k delta x1 plus k divided by delta x2. Right? Can you see it? Or the screen is... Can you all see it? More or less? And this is just having this equation and we got TP. A trick. If you did it correctly, you will always have positive signs. If you have some negative signs, have a look. Okay? That means something went wrong when probably remember that when you're computing the heat coming from the west, Fourier, the derivative is the gradient between forward minus backward. So P minus W. P minus W. And Fourier is minus thermal conductivity multiplied by the thermal derivative over space. So at the end you get always something like this. Now, in the code, I'm saying that this is B term, you will see, and this is C term, I think, but I will, now we'll see. Okay, so what is in the code? define the variables I will need to solve the problem. I will send you this. I will send you this as an example. So what I recommend you is, if you start using this kind of tool, you start modifying this. Because now all this algorithm that you see in the blackboard is structured here. So if you, okay, now I know the geometry is very simple. You just modify your geometry and that's it. The algorithm will run, will go. So I recommend you to include at least these 3 libraries. That helps you in file reading and writing. If you need to get something from a TXT file, for example, or write to a TXT file, that helps you if math is for, if you need to, let's say, do a square or do something, or a power, you need these libraries. Because this is a C console. I mean, this is not MATLAB, this is not OpenModelica, this is not prepared for doing this. This is prepared for doing anything. So, and this is the good part. You will have full control of your model. I completely hate black box models. I don't like it. That's why I don't like CFD. Can you control what is happening inside the solver of a CFD? You cannot control them. Presto or Quick or whatever. You play run, you go for a beer, you come after a few hours, you have one result. Okay, but how does the CFD calculate? Yeah, you can search for literature and it will give you a lot of integrals, a lot of... but are you controlling the solver? No, you are not controlling the solver. There are hundreds of people programming the solver for you. But you have to trust the results. Now with this, we are going from scratch, from nothing. You start building. And that's the good point, you can control everything. And if you want to add one physics, you add it. You think, okay, what is the best way to add this physics? But that's why it is very important that you understand the logical and the structure of the algorithm. Then you can implement everything. Of course, it has limitations. The main limitation that this has is that we can only go for structured grids. I mean, the good part of CFD is that you can put one car and it will create a mesh, different nodes all over. Here, you see how we are defining the nodes. If the domain is not, say, regular, it's tough to do it. If the geometry is complex, it's tough to say to the model which sort of shape has each node. Okay? But if you can simplify and go for basic geometries, then you have a good tool. So you include these libraries, then you start the program. In this case, we have just single program. With C, you have the option of, you have a main program, and then you can call to auxiliary programs. Like, you can calculate one program to, you can create one program to calculate heat transfer coefficient, for example. So you pass to the program temperature of air, temperature of solid, and noise correlation, and it gives you this. So from the main program, you can call auxiliary programs if you want. Or you can put everything in the main, up to you. This, because it's very simple, is everything in the main. Okay? Now I need to define, now this, forget about this. This is a command, so I will interact with a TXT file, which is, and the command to interact is trans. Okay, forget about that. Now, this is the definition of the variables I will need. Forget about you can put a static or not, depending on how much memory do you have in the computer. If the variables can be Boolean, if it's 0, 1, can be integers, if it's 0, 1, -1, -2, but cannot be 2.5, for example, integers, or can be float if they have 8 decimals, or can be double if it has 16 decimals. In this case, I put 16 decimals, but it was a mistake because I don't need 16 decimals. So we can put here actually float, which is This because I don't need it. I usually put a static double just in case I need it. Yeah, maximum error, yes, probably double. You can define as you like, but keep in mind that if you put int, that means those values, I, can only be 0, 1, 2, minus 1, cannot be 2.5. But I, for us, it's the index that is saying to me where am I in the space. It can be or node 0, or node 1, or node 2. It cannot be node 2.3, right? That's why it's integer. Okay, we start from the beginning. Float, that means 8 decimal values. I required from the memory a space of 200 values for temperature. So that's what I ask to the memory. Okay, reserve for me a space to write values of temperature, 200 spaces, please. And the name will be t. The vector will be named t. This value has to be higher than n plus m. Right? I have n number of nodes in the solid A. I have m number of nodes in solid B. So the total number of nodes that I have is n plus m. If I put here now n equal to 500, it will crash. Because I have only reserved a space for 200 values, and now I'm adding 500. So just you put whatever number you like in n and m, but it is important that you have the space required to host all these values, right? This is the solution map of temperature. This is the assumed map of temperature. I will have to compare one map of temperature against another map of temperature, right? So I need to store the values of solution in one array, and I need to store the assumed values in another array to be able to compare it.
Okay, so sorry, this is just a vector or a matrix?
This is a vector. Well,
Okay.
it's a matrix of one dimension,
Okay. Okay.
right? Yeah, if the problem was 2D, you will have two dimensions here. Okay? But now it's 1D. If we have time, and I think we will have, I will show you more complex software that I can discharge, and then you will see how we go. Before it was static here. Okay, static stands because sometimes the RAM memory that you have is not able to host all the space that you have required. Now you say, how? If 200 values, there's nothing. But if, for example, in a 3D transient problem, you will have a matrix of 4 dimensions. Temperature will depend on X, on Y, on Z, and on time. So a matrix, imagine I want to compute, I don't know, 2 hours every second. So I have one dimension is 7,200. And depending on the geometrical number of nodes, I will have matrices of a lot of elements. Each element requires certain bytes to be stored. Depending if it's double or it's float, you require more memory or less memory. If you are working with huge matrices, then put a static. And then the software will use part of RAM and part of your hard drive. Okay? Now, so we understand what this is the solution vector, this is the assumed vector. Now I need to define thermoconductivity as a float, because now it's 5, but thermoconductivity can be 5.5, for example. Density I don't need it for this problem because it's not a transient, but we will see it probably in the afternoon. Heat capacity the same. QB, I need to define QB. Heat transfer coefficient, I need to define heat transfer coefficient as a flow. Maximum error allowed, 10 at the minus 6. I put double just in case. Because maybe I want 10 at the minus 9. Then it's 9 decimals. And float cuts at 8 decimals. Delta x1, delta x2. I need to define them. So the software knows that there will be one variable named delta x1 that the type of this variable is a double. Okay. Float, air temperature, I need to define it. Relaxing factor, I need to define it. Integers, I need y to know where am I. The position is the index that gives me the position inside the wall. J stands for the number of iterations. It's also an integer. I can be in iteration number 0, 1, 2, 3, but I cannot be in the iteration number 2.3. So it's an integer. Max number of iterations, that stands, so I let the computer go until it's 100,000 iterations. If after 100,000 number of iterations it doesn't get the solution, it quits. Because otherwise, sometimes if you not reach convergence, the program stays over there. No, I want to, okay, if you are not able to get the solution of this simple problem in 100,000 iterations, it's because there is something wrong. So go out. I will explain you how to program this. N and M. Number of nodes in the A material, number of nodes in B material. And that has to be integer. Right? Error. So when we compare the two arrays, the solution and the assumption, I will need two variables. One is error total and the other one is error. I will explain you how they work. Then I have A, B, C, and D. As yesterday we have AW, AE, BP, and so on, remember? So it's to group coefficients. I will use A, B, C, and D. And I need thickness of the part A, thickness of the part 2. So I'm just translating what was in the problem. Okay, this is the definition of the variable. Now, forget about this. This is just, I'm open, file open, a txt file named 1D wall std, and I will write on that txt file. Because I will write the solution there. Okay. Do you have knowledge on C, more or less? No, nothing? Okay, it's very simple, and the good thing is that everything is here now. So you just, if you want to use it, you just have to modify this. Syntax is very simple. And one good advice in C is that the program is executed sequentially. So it starts from here, line number 8, 9, 10, 11, 12, 13, it goes like this. So if you put one command here, and let's say A equal to 0, and here A equal to 5, up to here A will be equal to 5. Because it's a sequential software. Okay. Now, first thing we have to do, input parameters. Input parameters, okay? We define. Tier is 25. Age, 10. Thermal conductivity, 5. Density, 1000. CP, 800. Whatever, we don't use it now. Heat generation, 500. Okay? Thickness, 005, 01. That's direct, right? This is physical properties and geometrical data input. Let's go to parameters input. In C, if you put dash asterisk and then whatever, it's commented. That means you don't execute this. Usually, this is because it's a simple model. If you are in a complex model, you need to type for you okay, keep in mind that this is whatever, or okay, starting this blog. I'm starting this blog. You need some comments sometimes because maybe you work here now with the model. You go to a conference, you come back and you say, wow, I don't remember now where we are in the model. So it's good that you put some notations for yourself. Also, if you are collaborating, you need to say your whoever you're working with what is in every part of the code. Now we define maximum error 10 at the minus 7 now, for example, and maximum number of iterations. In this case, 1 million. I put here 1,000, now it's 1 million. And relaxing factor equal to 1, because it's a very simple case. But we can put 0.9 if you want. Actually, we will play a little bit with that. And number of nodes, 10. M, number of nodes, 10. After every command, you have the semicolon. Okay, so in C, after you assign a value, you put semicolon. Okay. Another trick from C. There are few. I mean, it's very simple, but it's different if I say I equal to 0, or if I say I equal to 0. This is different. In this way, I assign the value of 0 to variable y. In this case, I am asking if the I variable has value equal to 0. Okay? So it's different. In this way, I force that the variable has 0. In this case, I'm asking. Okay? You will see how we deal with that. Now, after after I input parameters, let's say calculation of coefficients. Which coefficient do I have to calculate? Here, just 2. Those 2. Right? Because it's Cartesian coordinates, there are no areas, there are no different volumes. It's just, I need to compute how is delta x1 and delta x2. And by definition, delta x1 is thickness 1 divided by n, thickness 2 divided by n. Because it's sequential, if I put this line before this, it will crash. So here, I can compute this because I know what is thickness 1 and I know what is n. Because I have assigned a value for thickness 1 and I have assigned a value for n. If this line is here, nothing works. Because it's sequential. Okay? Great. So, after we have done the calculation of coefficients, I have to assume something. Right? The next step. We are here, right? Now, I need to create a map of assumptions. I don't have it. I need to create it. That's what I'm going to do here. Now, this is the first loop we see in the model. The loops that I am using are two kinds. The main one is for. How this works? For the index I equal to 0 until the index I is lower or equal to m plus m at one point in the value y. That means it will execute these lines for I equal to 0. Now, it will ask, is I less than m plus m? No. M plus m is 20, right? And I is equal to 0. Okay, then add one point to I and execute it again. Now it's 1. It will execute whatever is inside these claudators. It will execute again. 1. Now, same question. Now, why I is 1? Is this below m plus m? No. Add another value. And like this, until it's 20, 10 plus 10. Then it will move. So this is the loop. So it will execute n plus m times these commands. Okay? Easy? More or less, but it's okay, it's a language. But in 2 days it will be in your hands. So in this way we are doing, actually this line is this one. For all i's from 0 to n plus n plus m, I'm saying, okay, I don't have a clue of what temperature we'll have in the world. But I will assume that everything is at air temperature. Just to start. I can put here 1000 if you want, or 0, or minus 500, I don't care. It will converge anyway. The closer you start, the faster you will get a solution, of course. But sometimes you don't know where to start. Just start. The model will get the solution anyway. Okay? So now, what I recommend you is to start with some value that you know that it will be around. I mean, there will be some nodes that they will be close to 25. The ones closer to the surface, maybe will be 26, 27, they will be closer. So it's not a bad shot to start with 25. So let's start everything with 25. If you want, you can start here with a linear profile. Whatever you like. But it will take more or less, it will reach convergence anyway. Now, the map of assumption is here. Now, map of solution. Here, you can run the model without doing that. But if you say to the model before, give me this space for solution, 200 values for solution, it will fill with stupid values, even letters or signals or whatever. Because I will be inside equations, I don't want to have silly variables around. So I, let's say, put some value in this array, even I'm not going to use it. Just to make sure that there will be no stupid things in the calculations. Okay? You can neglect this if you want, but I'm using it. So in this way, I say assumption values are air temperature and solution values are air temperature. Just to start from something. Now, second step, let's go to the questions. Now I have one map of temperature, which is the assumption. Great, it works. Now, I will start with a loop. This loop will count for me the number of iterations. Because, as I told you, I will do this. I will do this. Right? Go from assumption, get a solution. Is the same? No. New assumption, solution. Is the same? No. New assumption, solution. Like this. Thousands of times. Until it's the same. When it's the same, you can move. But if you do this process more times than the maximum number of iterations that I am allowing to you, let's say 1 million, then move out, because we have some problems. That's why the loop stands for. So it will execute this, all the nodes, it will compare the error. Is the error higher? It's reasonable? No, you have to do it again. Okay, then J++. J is 1. Do it again. Is the error less than what you expected? No. Okay, go here. J is 2. Is this below maximum iteration? Yes, maximum iteration is 1 million. Okay, J equal to 2, and do iterations. Okay? Until, at the end of this loop, we have a break. So, you will see. Now, first thing we start with iteration is, okay, the error is equal to 0. I need to restart the error. So after the calculations, I can say, okay, is the maximum error between assumption and solution whatever? I restart this. Now, we start with the important part. The loop, geometrical loop. Now I have to explore all my domain. From the same, from I equal to 0 until I is below or equal n plus n, I plus plus. So now here the code will start I equal to 0. Okay, it will start equal to 0. If I is equal to 0, I am in the first node, yes, then enter inside. Because we have some equations for you if you are 0. If you are between 0 and n, you have another set of equations. If you are in n, you have another set of equations. If you are between n and n plus n, you have another set of equations. And if you are in the last node, you are in another set of equations. That's how we implement this that we have done for I equal to 3. You remember that we have 5 types of equations, 5 types of nodes. 1, 2, 3, 4, and 5. That's why we have 5 if. Because in case you are in the first type of node, you have to apply one equation. In case you are in the second type of node, you are in another set of equations. Okay? Now, let's start. I equal to 0, first node. Okay, let's do it, and you will see how I am doing with A, B, and C, and so on. How is the first node? The first node is adiabatic in one side and has conduction in the other side. Right? So it's like this. This is node P and this is node east. The question here is Q east and generation. Generation minus QE equal to 0. Correct? We don't have any more physics here. We don't have conduction coming from the west because it's adiabatic. So this is QB, it's 500 multiplied by the volume. The volume is delta x1 divided by 2 because it's half the thickness because it's in the edge. Multiplied by QB plus K TP minus TP divided by delta x1. Right? Applying Fourier because it's negative, it's leaving the node. Negative because it's minus K, it's plus. Okay, now we isolate TP here. TP is delta x by TE. No, K divided by delta x, sorry. Last QB delta x1 divided by 2 divided by K delta x1. Right? Now, I say this is C coefficient, this is D coefficient, and this is A coefficient. Because in this case, because we have only one conduction. If we have another conduction, we will have more terms in the denominator, as we had in the past. So, when I face one node, I usually say, the coefficient that came from the west, I name B, this is C, and this is D. And the denominator will be A. Okay, in this case, B is equal to 0, there is no B, because it's adiabatic. Right? C, it's K divided by delta x1. Correct? D, it's QB multiplied by the volume, half the thickness. A is B plus C. In this case, because B is 0, A is equal to C. But I usually put the denominator like A. In this way, I have the same equation for divided by A, divided by A, divided by A, for all the nodes. Now, temperature of the node, when I is equal to 0, it's equal to C, this coefficient, multiplied by the assumed temperature of node 1, my neighbor. TA, I plus 1. Because I is 0, this is the assumed temperature of the node number 1. Plus D, everything divided by A. This is how I implemented the equation in the computer. Any question? No? What will happen in the following node? In any node between 0 and n, if I is higher than 0 and it's lower than n, that means we are inside material A. We have, we have number 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes will be in this box. Number 10, no. Number 10 will be the one in the middle. But from 1 to 9, it will execute here. And because we are in the loop, it will execute from 0. Okay, it is 0? Yes. Enter here. It is 0? No. Go ahead. It is n? No. Go ahead. It will go until the end and go back. Now, is I below n plus n? Yeah, I is 0. Then add one value. I is 1. If I is equal to 0, no, I is not 0, it's 1. I is higher than 0 and n? Yes, go inside. It will execute. Correct? We will go here. Is I equal to n? No, I is 1. Go until it goes to the end. Now, is I lower than n plus n? Yes, I is 1. Then add another value, okay? I is 2. Now, is I, do you understand how it goes? Simple, sequential. It goes like this. It's but like this. Now, in case we have conduction from the west, B will have this time. I can do it, or you can do it if you want, but you will have this. B will be this time, C will be the same as in the other one, QB. Now it will not have half of value of the volume because we are we are not in the edge, so we have a full volume. The denominator will be B plus C, and my equation will be coefficient B multiplied by my neighbor, past neighbor, assumed value of T0, because we are in I equal to 1, plus a coefficient multiplied by east node, assumed value of node number 2 in this case, plus B, which is this term, divided by A. One can say, we have solved what is 0 here, right? Why, when we are computing 1, we are using assumed value of 1 minus 1, 0, and not solution value at position 0? Do you follow? Everybody? So here, I have calculated the temperature in the first iteration of node 0. So why? Okay, I got 0, but when I want to calculate node number 1, I need the temperature of the neighbors, 0 and 2. For the 2, I have to use the assumption. But for the 0, I have two options. I can use or the assumption or the solution. Never use the solution. Always use the assumption. Don't mix map of temperatures. If you mix, it can crash. Okay? So it always use assumption. I know that at this stage you have a more updated value because you have already computed. Anyway, you have assumed one full map of temperature. Use that map of temperature to create another map of temperature. Is the same? No. Go. You will advance. Probably slower, but you will advance. if you start mixing and part of the equation is using the assumed array and part of the equation is using solution array, no. Okay? So it will do that until n is higher to m. It will now execute in this loop. Now it's n is equal to m, then it will execute and say, is it lower? No, it's n equal to m. Then stop. Here we go. The question we have, for example, the question we have for the node in the middle, you will have B, this term, C, this term with different delta x. You will have generation of heat just in the half of the first delta x, but the equation has the same shape. B multiplied by the previous temperature, C multiplied by the following, plus an independent term divided by the denominator. Inside the second material, and in the last. In the last we have conduction coming from the west, convection, C is equal to H, but the same shape. Now we don't have temperature of the following node because there is no following node. You have temperature of air with H. Okay? Any question? No? Okay. Now, when I finish, this is the claudator that is closing the form. I mean, everything is executed up to here. I equal to 0, go up. I equal to 1, go up. I equal to 2. Now, when we finish that, it means we are here at this point. We have executed all the different equations for all the different nodes. Now we are here. Okay. Now I have to ask, we have a map of assumption and a map of solutions. Is it the same? How we do it? Then I comment myself, error calculation, just in case we have, I know there's some problem in the error calculation, I go just to this place of the code. Okay? Now, all this is to calculate the error. It's not like this because you have multiple variables and you want to check the maximum deviation between nodes. It happens that some nodes converge before some others. Like first shot we did 25, right? So I equal to, let's say 0, 5, 10, 15, 20, right? First, one in the middle, the one in the between two materials, one in the middle of second material, and last one, right? First iteration, first assumption, assumption 1. We said 25, 25, 25, 25, 25. We say that. Now we get a solution out of that. The solution was probably here we'll have like 50, 48, 45, 21, no, sorry, 27, 26, for example. I need to compute maximum deviation between them. Maximum deviation is 25 degrees, right? This is the maximum deviation. So I need to compare two arrays. So compare at position 0, compare at position 1, 2, 3, 4, 5, 6, up to 20, and the biggest deviation, that's the value I want to keep it. Because I need to ensure that this value is lower than 10 to the minus 6. That's why I'm doing this. So the error, so I need to explore all the domain. For 0, I equal to 0, it's the same form, the same loop. This is the loop I'm doing to explore all the domain. That's it. Now I have the solution array and I have the assumption. Let's try to compare it. Okay, from 0 to n plus m. I equal to 0. So let's start from the very beginning. Error is the absolute value between the difference between the assumption at position 0 and solution at position 0. In this case, 25. If error is higher than the total error is the value that will save the highest deviation. I will explore from 0 to n plus m, and I will compute different deviations. For example, in this case, first node has 25 degrees of deviation, but the last node only has 1 degree of deviation. So you keep with me, every node has different deviations. What I want to take is the highest. Error t, error total, will keep the highest deviation. And remember that at the very beginning we say error total is 0. We set to 0. We refresh the value. Now, the error we have calculated is higher than error total? Yeah, because error total was 0, it's the first deviation. Then, error total is the error. If not, keep like it is. Now, we are at 0. Go to position 1. Well, I is equal to 0. I is lower than n plus m? Yes, then add 1 point to I. I equal to 1. Go here. The error is the assumed temperature of node 1 minus solution temperature of node 1. Okay. 23. Is 23 higher than 25? No. Then keep 25. So in this way, after we explore all the domain, we will get the maximum deviation. Because if the node we are exploring has higher deviation than the total that we have computed, it will rewrite. Yes? Everybody understands? Or I repeat this? This is just to, because I have different values and I have to get the maximum deviation between them. That's why I have to compute one by one, and if what I am computing is higher than the maximum restored, okay, this is the new maximum restored. Okay? At the end, we say we are going to ask the question: is the maximum error that we have computed, the error total, higher than the maximum error allowed? I said maximum error. 10 at the minus 6 or 10 at the minus 7, I don't know. If it is higher, then I cannot go. I have to say, okay, now put this equation. I need a new map of assumption. And the new map of assumption is TA will be the solution multiplied by R. It's the same equation, but you multiply R and it's the same. If you cooperate a little bit, R, remember 0.9, 0.8. In this case, is 1 because it's very simple. But and because it's 1, this is 0. 1 minus R, 0. So new assumption is a solution. If R is not equal to 1, and I am relaxing a little bit the model, then R will stand for a combination between solution and old assumption. Okay? In this way, also with a loop, because I have to do it for each node, I will get a new assumed map of temperature. Now, is the error below maximum error? If this is the condition, then break. We finish. We can go. If not, we are not going to break the 4 at the very beginning. This is breaking the 4 here, where we started. This is the 4 that is accounting for the number of iterations, right? So this 4 has 2 ways to quit. Or because of the break, because we have reached convergence, or because it's doing loops and loops and iterations, and we say, okay, you haven't achieved after 1 million iterations, go away. We have something wrong. There's 2 ways to quit this array. This loop, sorry. Okay, now it will go here. If it's not the case, if it's not the break, now we have a new map of assumed temperatures. This, it will go to the loop and say, J, we are in the first, J equal to 0 in the first iteration. Is 0 below maximum number of iterations? Yeah, maximum number of iterations is 1 million. You will have to run. Okay, J equal to 1. Now, we reset error total and explore again the domain and by the equations. We are doing this with the new assumed map. Clear? Yes? Any question? Good. Then, if we are lucky, not lucky, if we get convergence, then we can do extra calculations like amount of heat or whatever, and print results. In C, you can print results on the screen, or you can print results in a file. If it's in a file, it's fprintf, file printf. Where you are going to print the file? In the file type trans. Remember that at the very beginning we say the file communication will be with the command trans. And trans is open a txt file named 1d_wall_std, and what I'm going to do with this file is to write. I want to write. That's why it's trans in the fprintf. You will have this, so you will not get from the... You just modifying this, you will get whatever you like. Now, I want to get T1, which is temperature, actually it's T0. I would like to print, I mean you can print whatever you like, but I am printing the first node, the node in the middle of the two layers, the temperature of the surface, and the number of iterations that I have required to solve this problem. Then the way to, because it's in blue, that means this is like titles. -n means we are going, I have to say it in English, line? Yeah, okay. Now, I will print a float, which is the t at position 0, t at position n, t at position n plus m, right? First temperature, temperature in the middle, temperature at the end of the wall, and a j, the number of iterations. That's a float with 2 decimals, a float with 2 decimals, a float with 2 decimals, and an integer. Okay? In internet there are plenty of libraries and blogs and tools to help if you have any difficulties on that. Now I close the file and I will print to the console, to the C console, finished. Just to make you know, okay, it's finished. Let's execute that. In the div C++, you just need, other than typing on this sheet, you need to compile. That will check if there is any error or something. There is no errors, there is no warning, everything is okay. If, for example, I told you that every line has to end up with a semicolon. If I delete one semicolon, hey, we have an error. I cannot compile, I cannot create the executable file. So, or if, for example, I don't define, imagine instead of thickness 1, I put thickness 3. And I execute the same, hey, error. Thick 3 is undeclared. I have not defined thickness 3 at the top. So it will start yelling. Yesterday and today I have talked a lot about the benefits of this method. But there are also drawbacks. The drawbacks is that sometimes you want to crash the computer. And if there are several lines, it's easy that you have some errors. Like these silly errors. Or instead of 1 plus, you have 1 minus. And everything crashes. Because it's a risk. You are building everything. So since you are building everything, you can do a mistake everywhere. I will maybe this afternoon. This afternoon I will explain you how to debug problems a little bit, and how, because sometimes here is easy. The code is very simple, but I have codes of thousands of lines. You have one error. Where is the error? I don't know. So there are ways to get the error. Okay? And with this button you compile. With this button you compile and execute. So we are executing, compile and run. Finish. Like this. Like nothing. And now we can open the file that has been created now at 11:33, and this is the file. We have run 25,000 iterations. Like nothing. This is very simple. But anyway, 25,000 iterations. Solution is that first node is at 28.12, in the middle 28, the last one 27.5. Okay. What happens if, now this is without relaxing. Remember, R was equal to 1. Let's change, let's play a little bit. If it's, let's say, 0.7, hey, we have a problem here. Yeah, I don't know what's the problem here now. But we have the same, mostly the same results, right? If we start, let me check what is happening.
Once we increase the error margin,
Yeah, I see. I will go for that one. That's why. No, that was, you see, we had problems because we just reserved 8 decimals to temperature, and it requires more.
the error was fine.
Yes,
Content.
probably error was lower than that and was moving in the area, so that's why. So we relaxed a little bit, and we got few more iterations. Remember that with a relaxation we have 25,000, now we have 29,000. So the more you relax, the more iterations you will require. But you will be in the safer side. Okay? Now we can say the effect of having, I don't know, more nodes. Let's say instead of 10, let's go 50 and 50. You see, it's 1.8 seconds to run 100 nodes. So it's doing 100 nodes. Let's see how many times. 38,000 times. No. 300, almost 400,000 times. But results are more or less the same. Can we even increase more? It's 28, 27.9, 27.43. Yeah, we can go up to 200, right? We cannot go more than 200 because we have keep 200. But one thing. If I put here 100 and 100, it will crash. And it will crash because the computer has saved for me 200 positions. But I am using 201 position. Because I have I equal to 0. Right? So then, if I'm using 100, I have to say here 1, 201, 201. Run. Okay. One thing is that, as you may get, this value, delta x1 and delta x2, depends, in the denominator is the number of elements you have. So, if thickness is low, and you want to put a lot of nodes in that, that means that this value will be extremely low. Right? And if this value is very, very low, keep in mind that in the equations, this value is in the denominator. So you can have numerical problems. That's why sometimes the solution is to add more nodes. Okay, but sometimes no. Sometimes you have to be realistic. Not because of adding more and more and more nodes, it's better. No. Because you are having tiny numbers in the denominator. If there is a trunk error or something like that, then everything will crash. Okay? Any question? No? Then, yeah, and we can play here if instead of 500 we have, I don't know, 5,000, we can see the effect. You see, we have too many nodes now for this space. 12 seconds to run. You see, the temperature has changed a lot because there is 10 times more heat generation. Questions? Nothing? We see them this afternoon because I would prefer not to start the transient algorithm now. So now everything we have done is just the solution is a picture. So everything we have done until now is, okay, we have a problem, we don't know what is the thermal distribution, and all this is just to get this picture, this line. Usually we don't go for the simple. Usually what we are interested in is in the evolution of something. Then we need to compute over time. So in the afternoon we will explain you how we create this in case the solution is not a picture but an evolution. Okay? Okay. It's a 3, right?
Yes.
I will send you now the two examples, the one with the steady and the one with the transient, so you will have it. And also the slides from yesterday, so you can have the links to download the Deep C++ and the Lezione. Okay? I think I have your emails here. Actually, do they have to cross?
Yeah. Valentina, Stanza,